Welcome to Your Math Explained, where we make math simple and clear. My name's Angela. Now that we have the basics of deriving trig functions, we're going to start taking a look at some derivative problems that relate to trig in a more complicated way. We'll also explore a couple of exam-style questions that relate to the AP and IB curriculum. Now before we dive in, if you haven't subscribed to the channel yet, make sure you do that first so you don't miss out on new weekly content. We're going to get started with a word problem, so take some time to read through this and make sure you understand what it's asking. Now, when faced with a word problem like this, your first step should always be to draw a diagram to represent the situation. So in this case, we have a vertical wall, and then we have a 10-foot ladder that is resting against this vertical wall. So let's say this red line here is going to be our ladder, and we're going to label this because we know that this is a 10-foot ladder. And now the angle between the top of the ladder and the wall is going to be theta. So that means theta is right over here. And then we have our ground, which is right over here. We were told that the bottom of this ladder is sliding away from the wall. So that means we're going away from the wall in that direction. And the question is, how fast does the distance between the base of the ladder and the wall change with respect to theta when theta is pi over 3? So let's go ahead and call the distance between the base of the ladder and the wall x. And note that as the base of the ladder slides out, the ladder is going to get flatter and flatter. It's going to look like that, and then if it slides out more, it's going to look like that, which means the angle here is going to be increasing. So the question here is not what is the distance between the base of the ladder and the wall when theta is pi over 3. It's asking how fast does the distance between the base of the ladder and the wall change. So we're not looking for x when theta is equal to pi over 3. We're looking at the change in x with respect to theta. So in other words, what we want to find is we want to find the change in x with respect to theta. So dx d theta is what we're looking for. So if we want to find dx d theta, the first thing we're going to do is write a function for x in terms of theta. And right now we're given three pieces of information. We have our theta, we have this is our x, and we have this is equal to 10. So something that relates all three of them is the sine function. So sine theta is opposite over hypotenuse. That means we would have sine theta is equal to x over 10. So this means if we isolate x, we get x is equal to 10 times sine theta. And now we have our function x in terms of theta, so then we can go ahead and take the derivative of x with respect to theta. So then we get dx d theta is going to be equal to 10 times cosine of theta. And now the last part is to figure out what dx d theta is when theta is equal to pi over 3. So that means the only thing left to do now is to substitute in the value pi over 3 into theta. And notation-wise, we would write this as dx d theta evaluated at theta is equal to pi over 3. So this is going to be equal to 10 times cosine of pi over 3. And cosine of pi over 3, that's one of our special triangles. So this is equal to 10 times 1/2, which means dx d theta is equal to 5. And lastly, we need to make sure that we put in our units for this. So the unit for x here is feet because our distance here is in terms of feet. And then our theta here is in terms of radians because we're given theta is equal to pi over 3, which is in radians. So the final unit here would be feet per radian. So what this unit here means is that at this particular moment in time, for every 1 radian increase in theta, the base of the ladder is moving away from the wall at a rate of 5 feet. Now for our second problem, we want to find the equation of the tangent to f of x at x is equal to pi. This is a very common AP style problem involving product rule. So you should know by now that to find the equation of the tangent, we need to first find f prime of x. So let's go ahead and start with that. And if you need to, you can rewrite f of x. Instead of having the square root x, we would have x to the power of 1 over 2 That way we can use our power law to find the derivative. So now f prime of x is going to be equal to the derivative of first function, which is x to the power of 1 over 2. So that's going to be 1/2 times x to the power of negative 1/2. Multiply that by our second function, so that's sine x. And then we're going to add x to the power of 1/2 multiplied by the derivative of sine x, which is cos x. At x is equal to pi, there are two things we need to find. The first thing is we need to find our point, and we can do that by substituting in the x value into the original function f of x. That means f of pi is going to be equal to square root of pi multiplied by sine of pi. And sine of pi is just equal to 0. So this is equal to 0, which means our point is going to be pi, comma, 0. Now the other piece of information that we need is the slope. And to find the slope, we substitute in x is equal to pi into our f prime of x. So we get f prime of pi is equal to 1/2 of pi to the power of negative 1/2 times sine of pi plus pi to the power of 1/2 multiplied by cosine of pi. So the first term is going to be 0 because sine of pi is 0. And cosine of pi is equal to negative 1. So therefore, f prime of pi is equal to negative square root of pi. And now that we have our point and our slope, we can use the point-slope form to write down the equation of the tangent. So the equation of our tangent line is going to be y minus 0 is equal to negative square root pi times x minus pi. And then we can just go ahead and simplify that a little bit, which becomes y is equal to negative root pi x plus pi root pi. And that would be the equation of the tangent line. And now for our last example in this video, we want to show that the derivative of this expression here is equal to this. Now this is a very common IB problem in which trig identities also needs to be incorporated. We start with d by dx of our expression, which is cos x over 1 plus sine x. Here we know that we need to use our quotient rule. So this is going to be equal to the derivative of the top function, which is derivative of cosine, that is going to be negative sine x, multiplied by the bottom function, so 1 plus sine x. And then we're going to subtract our top function, which is cos x, multiplied by the derivative of the bottom function. And the derivative of 1 plus sine x is just cos x. And then we're going to take that and then divide it by the bottom function squared. So that's going to be 1 plus sine x all squared. Now let's go ahead and expand out our numerator. So we get this is negative sine x minus sine squared x minus cos squared x. And then the denominator, we're not going to expand that out. We're just going to leave it as 1 plus sine x squared. Next, we're going to factor out a negative sign from each term on the top. So we get negative, and then in bracket, we're going to get sine x plus sine squared x plus cos squared x. And this is just so that we can now see that there is an identity here that we can use. Mainly, it is going to be the Pythagorean identity. So if you recall, the Pythagorean identity says that sine squared x plus cos squared x is equal to 1, which means we can go ahead and replace this with 1. So this gets simplified to negative sine x plus 1 over 1 plus sine x all squared. And now we can cancel out a factor of sine x plus 1 from both the numerator and the denominator, which means we end up with -1 over 1 plus sine x, which is exactly what we're trying to show. So this is where we would stop. And now let's do a quick recap of what we covered in this video. We started with a word problem and saw that we needed to pay particular attention to the variables being used so that we know what is the independent variable versus what is the dependent variable. And even though we have now moved on to calculus, identities from past trig units are still very important because they help us simplify complex-looking derivatives into elegant results. And lastly, always remember how to solve your trig equations, from reference angles to standard positions to special triangles and special values. And now it is your turn to give this a try. Can you find the solution to the word problem on the screen here? Make sure to leave your answer in the comments below and let us know what other calculus topics you'd like to see in the future. That's it for this video. If you found it helpful, remember to hit that like and subscribe. And if there's a topic you'd like us to cover, make sure to drop it in the comments.